All right, students, I got another great question from, again, from the hard book, and it's this hard material, Faraday's Law. So we're talking about some of the hardest material and the harder book. So not a surprise, getting a lot of questions from this one, and let's just kind of run through this. It's chapter 23 in the college physics book, but in the university physics, it's chapter 13 of volume 2, and it's number 35. And of course, these are picked out of your book because these have some calculus in it here. And so what I'm going to do is write down an equation, EMF equals, and I guess it's equation 23.2 of your college physics book. And it says this. It says the EMF is negative. The number of turns in the loop multiplied by the rate at which the flux is changing. So when you say that in words, you say right here, how does the flux change with time? Now, going back one equation, 23.1, the flux then is the magnetic field times the area of the field times the angle between the fields. And so I'm going to put these two things together plus some calculus. So if I were to change this and take the limit as delta t goes to 0, it would look like this. It would say the EMF, or why don't I just call it then the voltage, V, that's created is equal to negative the number of turns, and then I would have the time derivative of the flux, B A cosine theta. And so let me start there, because that really is the hard part of this particular problem. Then it's just a matter of plug and chug, although I shouldn't say that simple because we got some calculus to do here, okay? Actually, now that maybe I should read it, because maybe I don't even need to do this much. It might just be flux, because I read that first sentence here. So it says, the magnetic flux through a loop shown in the incumbent varies according to this equation. Okay, so I guess I don't need this. Okay, that makes it a little easier. But I do want to write then this formula in its calculus form. Would be the derivative of the flux, okay? And of course, they then, in the problem right now, just gave me, it varies according to this, where phi sub m is in Webers. What is the direction and the magnitude of the current in the 5 ohm resistor at these different moments in time? Now, I guess I should also then point out that, at least in the picture, and they don't explicitly saying it, but it looks like they've got one loop. Let me grab some yellow pad over here. Okay, it's kind of out of my reach. But let me get it close by, because I see that I'm going to need a couple pages for this. But the first step I would do is to apply Faraday's law, which says this is how you get the voltage. This is how you get the EMF. And so I'm going to put a negative, and I'm going to put one loop, and then I'm going to put the time derivative, and I'm going to put the equation that they give me, 2 times, well, maybe I should just drop the times, 2e to the negative 3t sine 120 pi t. Okay, and they're asking for the current. Now, before I actually do the derivative, let me also then point out that Ohm's law, which we learned, wasn't last chapter, two ago, either 2 or 3 chapters ago, says take the voltage and divide it by the resistance. So this is the voltage. So this is the new stuff here in this chapter, Faraday's law. And this is the Ohm's law of how we're going to get the current. And so I'm going to put those two things together. Okay. So it would look, I guess, something like this. Current equals voltage divided by resistance. The resistance is just 5 ohms. Okay, so I'll just make that easy on myself. And the flux is, as they are describing, and I think that's why they put this little loop here, kind of give us a visual picture. I don't know if they explicitly said this is the flux only in this circular part, but it looks like in the picture, as the wires come out here, there is no more field. See, they've got this B field over here. So I think we're fine to just say this is the total flux, whether it includes this part or not, or this little gap there, this is the total flux. So using this, I'll put here a negative. I won't worry about the 1. But then I'll have the time derivative. And I'll take my first step by saying derivatives, you can just pull constants. So I'll just pull the 2 out in front. And then I've got e to the minus 3t sine of 120 pi t. So I think one of the things that make this problem hard is this step right here, just getting here, where I had to put together Faraday's law with the calculus and then put that together with Ohm's law. And so putting those 3 together, now I can do the math. And that's the second hard part of this problem is now I have some pretty good math to do because I got the derivative of a function that involves 2 factors of time. We called this the product rule. And let me just work that out. Maybe I'll start with just simplifying this 2/5 right here. So that's a negative 0.4. All right. Then the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. So let me take the first times the derivative of the second. So the derivative of a sine is a cosine with a chain rule giving me the derivative of the argument. So there's the first times the derivative of the second. And then it's the second times the derivative of the first. And the derivative of an exponential, natural exponential, is a natural exponential. And then the chain rule is negative 3. Now, if I simplify this, let me grab a calculator here. This first term, I've got 120 pi here. And I'm going to multiply it by my negative 0.4 when I do a distributive here. And so this is going to give me a negative 150.8 e to the negative 3t cosine 120 pi t. So that's the first term. And then here it looks like I've got a negative 3, and that's it here. And then the distributed is a negative, another negative, and then 0.4. So that makes a plus 1.5. Oh, sorry, 1.4. 1.2. And then I've got the e to the negative 3t, and then the sine 120 pi t. So there's my 2 trig functions. and the coefficient of 150 really dominates. So most of it's controlled by this one. However, because it has a cosine function, this could actually get kind of small when this one's not. So this term could be bigger. So I don't want to say I could ignore this one. But if you're at say 45 degrees where the sine and cosine are equal, and these are already equal, this one's going to dominate here. But that's the big step. Now I can actually answer their question, and I'll do part A. So part A is set this equal when time is equal to 0. Okay, so if I set time equals to 0, cosine of 0 is 1, e to the 0 is also 1, and so this was a negative 150.8. This here, sine of 0 is 0 times anything, and so I guess I'm kind of done with that one. Now, another one is 2.17 times 10 to the minus 2. And maybe since this goes to the same, maybe I'll put 120 pi times 2.71 times 10 to the minus 2. And I'm kind of curious if anything's kind of interesting about that one. Why don't we just do 120 times 2.17 times 10 to the negative 2 and see if we get an even number. We don't. We get 2.604 pi's. So it's not exactly a pi or 2.5 pi, because the sines and cosine functions are kind of interesting when you have 1 pi, 2 pi, 3 pi, 4 pi, or half pi, 1.5 pi. So we're kind of in between. So let me not, do anything fancy. Let me just get a decimal here. And so this is 8.181. How about we do that? Be easy to remember too, 81. Okay, so then to get the current, it would be a negative 150.8 times e to the negative, well, maybe I should do that number too. What is negative 3 times 2.17 times 10 to the minus 2? So negative 3 times 2.17 times 10 to the negative 2 makes a negative 0.0651. Yeah, move that down so you can see it a little better. Okay, so again, don't know if there's anything real exciting in here other than, like I said, plug and chug. So this would be 0.0651. And then this would be cosine of 8.181. And this other term here would be the plus 1.2 e to the negative 0.0651 sine of 8.181. Now, the other thing I should be a little careful with is, if you'll notice, they gave us in terms of seconds here, in time. And so this is a real number, if you will. That's a way of saying indirectly this must be radians. And that would be easy to overlook, especially since I know that my calculator is in degrees. So let me switch that over to radians. Okay, so this first one, I guess, would be the negative 150.8. Multiply that by e to the negative 0.0651. Multiply that by cosine of 8.181. And why don't I just do that first term? So this one comes out to be 45.39. And then I'll do this term, 1.2 times, and then we got E again. So E to the negative 0.0651 times sine, and there's the 8.181. Okay, and then this is a plus also. Yeah, much smaller, but it's worth including. So 1.06. And then so finally let me put the two together, copy, paste, and it looks like we're at 46.45 amps here. Okay. And again, more plug and chug here at 3 seconds. Now, 3 seconds is going to be very interesting because, first of all, the 120 pi times 3 seconds is an integer number of pi's. So 300, this is 360 pi's. Now, I say that is interesting because if you remember your sine function, like this, every integer of pi is a 0. And so 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. And so your sine function is going to come out to be 0. Now, maybe I need another page to finish this. But this equation for current, which has 2 terms, and the second one having sine in it, that one is going to be 0. So I can have something plus 0. Now, the other one, if you remember in a cosine function, one pi is here. That gives you a -1. And 2 pi gives you a +1. 3 pi gives you another -1. And 4 pi gives you a +1. So in other words, odd numbers of pi are going to give you a -1, and even are going to give you a +1. And so we're at 360 pi. That's even. And so this term right here, cosine of 120 pi times 3 seconds, is going to be a +1. And that means I can just put here negative 150.8 times e to the minus, and then putting in my 3 seconds here for the time would be a -9, and my cosine would be just a 1. Like, it might be kind of nice just to try that. Let's see, cosine of 360 pi. Yep, +1. All right, so we can, if we notice that with our trig functions, we can save ourselves a little work. And e to the -9 is going to be incredibly small. It's exponentially small. So this is going to be really small. In fact, I'll just do that one by itself. E to the -9. Yeah, see, 10 to the -4. So by the time I multiply it by a -150.8, it's still pretty small. But I guess not 0. So keep that in mind. And so you can just see that the equation for the current, decays away exponentially. So 3 seconds, it's almost completely gone. So this is a decaying function that's only going to last for, measurable amount of time, like 3. Well, you can measure that pretty good, 3. But, after 5 seconds, you might as well call it 0. Especially since at 0 time, we had an enormous current. So 3 seconds later, we went from a large 150, although in the negative direction, down to, well, still negative, but, you know, 5 orders of magnitude smaller. And then, oh, and that's it. All right, so that's it. So again, I think the big part was kind of having you do the calculus and then doing a product rule, and then the rest is just kind of plug and chug into your mathematical equations. All right, hope that helped. Bye now.